Welcome to your lesson on quadratic sequences. Please get your notebook ready. We're actually going to do some of the problems from your homework problem set to get you started on that. Here's what the practice problems look like for quadratic sequences. We are going to do 1b, d, f, j, l, and number 2, a and b as well. So that should give you a really good start on the homework. It's going to do a good portion of these quadratic sequence ones here and get you started on the latter problems as well. There's a few more after that. Please try them all. Let's look at practice 5, number 1b. All right, here's the sequence. So I'm going to write the sequence here. Please get used to using these symbols and showing all this work. This process will get you to be stronger in this skill for sure. So first I'm going to find the first difference. From -7 to 4, you have to add 3 to get there. From -4 to 1, it's adding 5. From 1 to 8, it's adding 7. And from 8 to 17, it's adding 9. So that's our first difference. Since this first difference is not constant, we know this is not a linear sequence. Now to check if it's quadratic, we're going to do the second difference. To get from 3 to 5 is 2, and 5 to 7 is 2, and 7 to 9 is 2. So the second difference is constant. That tells us this is quadratic. So since this sequence is quadratic, we're going to fill this little table. Here's our n values: first term, second term, third term, fourth term, fifth term, and the term value at each of those. So basically at position 1, we have -7. At position 2, we have -4. At position 3, we have 1, and so on. So there's our sequence. But since we know this is quadratic, we're going to do n squared and see what we get. Quadratic must always have an n squared, right? So n squared, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So if this quadratic sequence was as simple as just being n squared, then that would be our sequence. However, this is the sequence we're given. It doesn't match this. So our sequence in this problem is a little more complicated than just n squared. There's more going on here. So we take a look now. We compare n squared to what our sequence actually is, and we see what's going on. To make a 1 into a -7, we have to do n squared, gives us 1, and then we have to subtract 8 to get there. How about this one? We have n squared, which is 4, and to make it a -4, we have to go from here to here and go -8. And here we have n squared is 9, but to make it a 1, which is the actual number in the sequence, we have to subtract 8. So it looks like every time we have to subtract 8 to get from n squared to our actual sequence. So we have n squared plus some value gives us what we need, right? In this case, it's n squared minus 8 every time. N squared minus 8, n squared minus 8, n squared minus 8. So it's a pretty simple pattern, n squared minus 8. So if every quadratic looks like this, which is basically quadratic in standard form, right? The squared thing, the x thing in a normal quadratic would just be x squared, x. Anyway, it's standard form. We know that the first portion is just n squared, because n squared produces this number. The second portion, which actually has a linear form, is going to be whatever else needs to be done. In this case, all we do afterwards is always -8. Doing that gives us the value we need. So our final rule is n squared minus 8, because n squared minus 8 every time gives us the number we need. Let's look at the next one, 1D. So here's our sequence, 2, 6, 12, 20, 30, 42. So 2, 6, 12, 20, 30. I'm going to find the first difference. From 2 to 6, it's 4. From 6 to 12 is 6. 12 to 20 is 8. And there's a 10. Again, it's not linear because these are not constant. So let's take the second difference. And in this case, oh, that goes up by 2, by 2, by 2. It goes up by 2 every time. So let's fill in the table. Here's our sequence. Again, term number 1 is 2, term number 2 is 6, term number 3 is 12, and so on. Let's do n squared. N squared will always be the same, right? 1 squared is 1, 2 squared is 4, and so on. Now again, if this quadratic sequence was the most simple case, it would just be n squared, and this would be our sequence. But our numbers in the actual sequence are not that. So we compare. What has happened to n squared to make it a 2? So we have n squared plus what number changes it to 2? Well, in this case, we're going to add 1. And here we have n squared, and now we're changing it to a 6. So n squared plus 2. Plus 2 will make it a 2. Here we have n squared is 9. Plus 3 will make it 12. Here we have 16 plus 4. And here plus 5. So n squared plus 1, n squared plus 2, we know that we have to do n squared plus these numbers to create the actual sequence, which is here. So you look at those. Now you got to look at this as its own sequence. All right. This is some kind of sequence. Something's going on here. So we had the original sequence. Now we have this sequence, which is going to be the part we're adding to n squared. Let's look at this sequence on its own. I'm going to take the first difference here and see what happens. 1 to 2 is plus 1. 2 to 3 is 1. 3 to 4 is 1. 4 to 5 is 1. All right, so now we have a sequence where the first difference is constant. And if that's true, it must be a linear sequence. A linear sequence always looks like this, right? And the amount it's always going up by is the b value. Then this is always going up by 1. So really this linear sequence right here is 1n plus a. Now we're going to consider the a thing. Do we need more? Do we need to add more here than just n? So if this says 1n, then you look at this and you're like, 1 times n is 1. And what do we need to add here? 1. All right, let's look at the second one. And in here, we're going to put a 2 in here. So 2 times n is 2. And what do we need to add here? 2. So it's okay. Let's look at the next one. Using this simple linear sequence. 3 times n. 3 times n is 3. And that's all we needed to add to n squared here also. So it looks like we don't even have to worry about an a thing. Just adding n is enough. So again, here's our quadratic made up of two parts. The quadratic part, the linear part. In the quadratic part, we just had n squared right here. It gave us those numbers. And then the part that we're adding here is just the n value, right? 1n. Because this is 1, and then 1n is 2, and then 1n in this case is 3, and 1n in this case is 4. So just by adding 1n, we've gotten the numbers we need. So our final rule here is n squared plus n. Let's look at 1f. The sequence is 6, 14, 24, 36. Okay, let's put the sequence in here. Let's find the first difference. 6 to 14 is 8, and then 14 to 24 is 10, 12, 14, and so on. No constant, therefore not linear. Let's look at the second difference. Up to, up to, up to. All right, second difference is constant. It must be quadratic. Fill in the table. Here's our original sequence. Since we know it's quadratic, we're going to try n squared. Those ones are always those values. And now the same thing we always do. We compare n squared to the actual sequence. So n squared doesn't produce our sequence, so it's going to be n squared plus something. All right, we have 1, n squared is 1, but we need a 6, so it's going to have to be 1 plus 5. Here we have a 4, but this is 14, so we're going to have to do n squared plus 10. So again, n squared plus what number? Well, here we needed to add 5, here we needed to add 10, here we need to add 15, here we need to add 20, and here we need to add 25. So these are the numbers we have to add to n squared to make this sequence work. Looking at this, it's a new sequence. Let's check the first difference to see what's going on. That goes up by 5, up by 5, up by 5, up by 5. It goes up by 5 every time. So if the first difference is constant, it must be linear. Linear sequences always look like this. Bn plus a. The constant rate that it's going up by is your b value, so 5n plus a. Now a might be necessary or maybe not. Let's check. So 5 times n, we're going to check. 5n for each of these. 5 times n, 5 times 1 is 5, and that's the number we need to add. 5 times 2 is 10, and that's the number we needed to add. 5 times 3 is 15. That's the number we need to add. So it looks like 5n is enough. 5n produces these numbers, right? 5 times 1 produces 5. 5 times 2 produces 10. 5 times 3. So 5n is enough. So again, there's our quadratic sequence. Our quadratic portion is just n squared. That produces these numbers. And our linear portion is 5n, because 5n was enough to produce this part. So we have n squared plus 5n. So our rule is n squared plus 5n. Let's look at 1j. We have this sequence, 13, 22, 33, 13, 22, 33, 46, 61. First difference, 13 to 22, plus 9, 22 to 33, plus 11, 33 to 46, 13, and so on. It's not linear. Those are not constant. Let's look at our second difference. Oh, up by 2 every time. That tells us it must be quadratic. Fill the table. our sequence at first position is 13, at second term is 22, third term is 33, and so on. Let's do n squared. Since we know it's quadratic, this n squared is part of our rule. So n squared is 1, 4, 9, 16, etc. All right, same process. Look at n squared. Just squaring n does not produce the sequence. So that simple quadratic is not enough. We look at that, we say, hey, we have 1, n squared makes 1, but we need it to be 13 in the actual sequence. So that's going to be plus 12. Here we have a 4, but we need it to be 22. That's going to be plus 18. So n squared plus some number in each case. In this case, we're adding 12. In this case, adding 18. In this case, adding 24, then 30, then 36. So those are the numbers we have to add. We have to do n squared plus each of these numbers to get the one we need in the sequence. So now you look at these and you're like, all right, it's a sequence. Is there a pattern? Let's check. There is. It goes up by 6 every time. If it goes up by a constant every time, it must be linear. If it's linear, it takes this form. And the constant rate of growth goes in for B. So 6n plus A. Now let's check if 6n is enough. So in this case, we need to produce a 12. 6 times 1, which is n, does not produce 12. No good. 6 times 2 does not produce 18. So let's look for more. 6 times 1 is 6, but we need it to be 12. So we need plus 6. 6n times 2 is 12, but we need it to be 18. Oh, 12 plus 6. All right, so we added 6 both times. How about 6 times 3? 18. Plus 6. All right. So it looks like in our rule, we have the n squared part, then we have the 6n part, but 6n was not enough. We also need to do 6 times that plus an additional 6, so those are additional 6. That's how our linear portion looks in this case. So our final rule is n squared plus 6n plus 6. And here we can see that that linear part was not enough. We needed 6n plus 6 to create these numbers. 1L. Okay, similar to the last one. Let's see if we can do it. Our sequence is negative 4, negative 3, 0, 5, 12. First difference, 1, 3, 5, 7. Not linear. Second difference, 2, 2, 2. Quadratic, we see a constant here. Fill the table. Here's our sequence. N squared every time is the same. N squared is not enough. What does this need to? Goes down by 5. How about this one? It goes down by 7 to create the term in the sequence. This one goes down by 9. So there's a pattern here. N squared plus some number, or in this case minus. So n squared minus 5 produces the number we want. N squared minus 7 produces the number we want. N squared minus 9 produces the number we want. So here's the pattern. This is another sequence. Let's check what it is. Is there a pattern? Negative 5, negative 7. Oh, negative 2, negative 2, negative 2, negative 2. Constant. That means it's linear. Bn plus A. Our constant is negative 2, so negative 2n. All right, is negative 2 enough? So negative 2 times n, negative 2 times 1 is negative 2, but the number we need is negative 5. Negative 2 times 4, sorry, negative 2 times 2 is negative 4. Number we need is 7. Negative 2 times 3 is negative 6, but we need a negative 9. So let's go back to here. Negative 2 times 1 is negative 2. It needs to be a negative 5. That means we need an additional negative 3. Let's confirm here. Negative 2 times that is negative 4, but we need negative 7. That means we need an additional negative 3. So each time was an additional negative 3. So going to our quadratic rule, n squared, but here we had negative 2n, and that a is an additional negative 3, because these numbers are produced by multiplying this by negative 2 and then taking away another 3. So our final rule is this. Okay, 2a. There's this sequence. First difference, second difference, filling in the sequence, n squared. All right, find the difference here. Minus 19, minus 24, minus 29, etc. Check if there's this pattern. Yes, negative 5 all the way. Therefore, negative 5. However, negative 5 is not enough. It's negative 5 minus 14. And there's our rule. Last one, take a moment, take notes, make sure you understand.